Today we're going to talk about NERF. It stands for Neural Radiance Fields, and you can see the output of a NERF in the videos below. So you have a bench, you have a tree, you have a plant. And what NERF tries to do is it tries to model a scene that happened in the real world. It takes, like somebody took pictures of that scene at different view angles, at different distances of a certain object as well as the background. NERF learns from that and is able to generate new views from certain angles or distances that were never seen before. And what's really impressive is the level of details that you see in the leaves, for example, of the tree. You see the colors are really accurate. You see how light is able to penetrate through the leaves. You see the shadows. The transparency of certain things. You see how light gets reflected at the right angle. So it is as if the architecture, or in the architecture, it's able to mimic real world physics, and that's what we're actually gonna look at as we try to understand NERF better. So just to talk a bit about the title, it's a 2020 paper entitled Representing Scenes as Neural Radiance Fields for View Synthesis. So we're going to represent real-world scenes as radiance fields. So radiance field is basically any space where at every point in that space, we're able to determine how much light passes through that point. Or you can also say how much light got absorbed at that point. It could be the surface of an object, or it could be a free space, or whatever. And the amount of light that gets absorbed or reflected at that point will determine the color and the transparency. So radiance field is just another way to actually understand the colors and transparency of all of that. And we're not going to do that explicitly. So it's not going to be like a voxel voxel grid type or a mesh or whatever. We're not going to, for every point in that space, it's not going to output exactly the amount of light. We're going to use a neural network, a bunch of weights, to implicitly output the amount of light at that space, given the coordinate and how we're looking at that coordinate. And we're going to do that for view synthesis. So we're actually gonna, this whole thing will allow us to synthesize or render new views that were not seen before. There is a bunch of slides to explain this, and I'm gonna start right here. So the planoptic function is this sort of theoretical concept in computer vision where the goal is to actually describe at every point. You can think of those white points as like a sensor or any point in the space. We really want to know how much light comes into that point from all directions at that particular point. By summing all of the light rays that reach this sensor, we can determine all of the properties at that point. Now, this is a theoretical concept. Very difficult, very complicated to achieve, and NERF is going to actually try to get there to some extent. And the reason that's important, once again, determining the light tells us about the color and the density at that point, whether it's on the surface of an object or just in the free space. So from a very high level, the way we're going to model that is we're going to take the spatial location of a point in space. We're going to take how are we viewing that point. We're going to ask a NERF, which is a bunch of weights. It's actually going to be a MLP. We're going to ask the NERF, what is the light density at that point? And NERF will output the color and the density based on where we want to know that information and where how we are viewing it from. So you can think of it as a continuous 5D function. And what we're trying to do, we're trying to parameterize a 3D space in a network. And that 3D space will tell us how dense a point is in that space and the color it emits. And of course, it's dependent on the viewing direction because the color of any point, any specific point in space, depends on where you're looking at it from. One important concept just to talk about is the implicit representations. Let's say we're trying to model the shape of the head of a monkey, as you see here. And for every point in space, we want to know, are we inside the shape, the object here, or the head, or are we outside? So a coordinate-based neural network, it's one where we fit in the, let's say you have a 3D space right here, and for every point of that space, you want to know, are you inside the head or outside the head? And so the idea here is that what we're not doing, we're not actually storing the value of whether we're inside or outside the head explicitly. We're not trying to store that information for every pixel in that space. We're actually using a neural network that's going to tell us that information. And that is what implicit representation is about. So we don't explicitly store the value of the field at all the coordinates. We use a set of parameters, a set of ways to tell us that value. And here, the idea is that we're actually storing the geometry of the object in the weight itself. And that understanding will help us to better understand the NERF, where the NERF pretty much does the same thing. It's storing the geometry and the view-dependent appearance in a model implicitly, so it won't be explicitly. So let's go one level deeper and see how a NERF is modeled. So in a NERF, we're giving it the 3D location, X, Y, and Z. We're going to talk about the positional encoding a bit later, but that is an important point. It's just a pre-processing step for now. And this is one of the main parts, is this MLP right here. And in here, what we're going to do, we're going to focus on building the 3D geometry of the scene. So we're going to try to learn the density of every point in that scene, and that's going to give us the density value. There is a much smaller second part of the architecture where we're going to feed in the direction, and based on the feature vector that comes out of here, which is the learned 3D geometry, as well as the direction, we're going to focus on the appearance. How, based on the angle I'm viewing it at, how does the color change? How does the reflection change, or the transparency? And the reason why they introduced the direction much later in the architecture is that we don't want the model here. We don't want the 3D structure. We don't want the model to cheat. The model can overfit if it understands that from this particular viewing angle, the color seems to be, let's say, red or something like that. So it's not going to learn about the geometry. It's going to cheat and just say, okay, well, whenever the camera is from this angle, we'll just output this specific color, for example. So we're introducing the viewing angle much later to make sure whenever we focus on the 3D geometry, it's not overfitting on the training data. So this part right here is just, it's a more of a refinement where we're trying to add the view-dependent effects. So how are we going to train a NERF? So a NERF, we're going to take many images of a certain scene or an object. Okay, these are all the camera poses, as you can see here. So we're going to take many images from different viewpoints. We're going to learn how the object looks like from different directions and angles. We're going to train the NERF in order to generate new views that were not seen before. So what NERF is going to do is actually going to capture the 3D structure of a scene. It's going to store the light field, so how much light gets absorbed at every point in that space. And from that light information, we can render the geometry and we can render the color and the effects. Okay, so the question now is, how are we going to render new views? And we're going to show two techniques of the architecture that are very powerful because they, in a way, mimic the physics. And that's why we get these realistic effects. So what's going on here is that we're going to choose a camera position right here. We're going to look at the image that we're interested in, for example, and we're going to shoot a ray from the camera through a particular pixel that we chose, and we're going to shoot a ray all the way into some kind of a 3D space right here. And we can do the same thing from another angle. Okay, so same thing. We're just going to shoot a bunch of rays, and you can have like multiple rays from the same camera angle. And for every ray, we're going to sample certain points along that ray. So I have my points, and I have the angle at which I'm viewing it at, which is, for example, if this is the center, this is my angle right here. I'm going to pass these points to the neural network. I'm going to evaluate these points that I sample along the axis, and then I'm going to get the color and the density of that point of every one of these samples. So like if a point is on that attachment of the truck, I'm going to get different shades of yellow or orange, and here I'll get the color would be empty, would be nothing, or the density would be low, and whatever's on the attachment of the truck that would have a high density. I'll have all of this information across that ray, and the same thing for this ray as well. And what I'm going to do is that then I'm going to use volumetric rendering. I'm going to composite those points or aggregate those points. I'm going to project them back to this 2D image right here. This is the volume rendering. This is the ray that we shot it through the scene. I'm going to have the density. So if, for example, it hit an object right here, my density is going to be high. I'm going to get the color of that density. I'm going to take all of this information, project it back to the 2D. I'm going to do that for all of the rays that I shot through the image, so for all of the pixels. Once I do that, I'm going to be able to render a new image. Okay, and based on the image that I've rendered, which is this one, I do have my ground truth, and I just take the L2 loss. And that's going to give me a loss that I'm going to back propagate through the whole network, which is differentiable. And my model is going to be optimized in this way. So let's go over those components. So this is one of the two components that makes NERF really powerful, because through this component, it sort of mimics the physics of rays and how ray bounces with the surface. So we're going to create a ray. We need the position of the camera. We need an image, right, with pixels. And then we're going to shoot a ray from the camera location to every one of these pixels right here. The image, the object is going to be somewhere in 3D space, so there's going to be a 2D projection. And what we want to know is how light interacts with the surface. So the reflections, the shadow, the refractions, the global illumination, all of that is going to be analyzed by the NERF. So each pixel on the image, it corresponds to a ray that travels in the 3D scene, and the direction is determined by the pixel and the camera location. Once we do that, we're going to be able to sample the density and the color. So once we have those samples, we want to reproject that back to the 2D, and we're going to do that with the volumetric rendering, which is right here. So one important concept to know is that we cannot just use the density. We cannot just use, okay, at this point in space, there's an object, yes or no, because that's not going to give us that realistic effects that explains all of those nice things we saw. So to get realistic effects, you need to render light absorption, there's a typo here, probability. So we need some mathematical equations that are going to model how much light is getting absorbed as I cast a ray out. So how much light is received by these objects that are found along the ray. So we have three components right here. We're going to talk about the transparency, or the alpha here, which is the fraction of light absorbed at a specific point, taking into account the density and the step size. So you have a certain step size, a certain distance between one point and the other. And the density, it's about how dense is the object. And of course, the more something dense it is, the more it's going to absorb the light. Or if it's not too dense, if it's transparent, it's going to let some light pass through it, so it's not going to absorb too much. So this will let us know at every particular point in time how dense is the object right here, or how much light is going through the object. And this is a differential type of probability because it just looking at a very small comparison between this part and this part. But in order to do that, you also need to know how much light is received before entering that part, and that's what the transmittance is about. How much light has survived. So let's say you have a light bulb right here. It's shooting light all the way across the rays, and at every point, light is being absorbed here. It's being absorbed here. It's being absorbed here. So how much light? So every one of these point is trying to actually absorb some amount of light based on whether there's an object there or not. So if these points, depending on how much light they absorb, there's only certain lights, a certain amount of light left, and that is what the transmittance determines. It's actually cumulative probability that light is not absorbed as it travels along the ray. That's why it's a product of this probability right here. And that's why, for example, for things that are really far in the back, light doesn't travel as much. So you have so the light gets more lost as it's further along the ray, for example. So for just to explain the alpha concept a bit, so as if something's really dense, then your density is going to be really high. Exponential to the minus something really high, it gives you a very low number. 1 minus that number, it gives you a density that's closer to 1. Something that is in free space will have an alpha that's closer to 0. And the colors, so this is when we project it back. So this is the formula that allows us to project from 3D back to 2D. And it is the accumulated light along the ray, integrating both the opacity and the color properties of the scene. So based on all of the opacity and the colors, I'm going to aggregate them. So we usually need to take the integral because it's a continuous space, but to approximate it, we're going to take the sum of all the colors and the alpha for every one of these have an alpha, and we're going to get the transmittance. So the transmittance of this one times the alpha at this point times the transmittance of T2 times alpha 2 plus the transmittance of T3 times alpha 3, so on and so forth. And we're going to add all of those up. We're going to do a weighted average, and it's going to give us the color at that pixel. This is another illustration to explain the volumetric rendering. So we're shooting a ray right here, and we're sampling points. And let's say you have an object right here. So here the density is low. Here we have a high density. So once again, exponential of something minus a large number. We take the minus of that. We take the exponent. So it's going to be close to 0. 1 minus something close to 0 is 1, so that goes high. And that effectively terminates the ray. That's why when we shoot a ray, let's say there's an object right here, let's say there's an object behind it. Well, we're not going to see this object right here because the ray is going to terminate at that location. So this one's going to absorb all of the light. We're not going to see nothing behind it. So the density is going to go back to 0. When something goes back to 0, your transmittance is going to be 0. So as you're summing out, all of the transmittance from this point onward is going to be negligible. So all of these are not going to contribute to the color. So each sampled point contributes a portion of the color proportional to its opacity and the transmittance. And given the transmittance is like very low after a certain point, they're not gonna contribute. So the color is really the sum of all their contribution up to of all the points along the ray until we hit some kind of an object, regardless of where it is on the ray. So just to sum it up, we shoot many rays from a certain camera angle passing through our 2D. We're gonna see how it interacts with the object. We're gonna apply those formulas right here that I explained. We're gonna render those back to the 2D, and then we're gonna take our loss with the ground truth. It's an L2 loss. And we're gonna minimize the difference between the renderings and the image, and that's how we get the final NERF 3D model. However, for all of this to work, there is a necessary trick that we still need to do to bring everything together in order for the fine details to come out. But before I do that, I'm just going to cover the, just to show the architecture quickly. So the actual architecture of the NERF is just an MLP, bunch of fully connected layers. So you have your input right here. It goes through about 1, 2, 3, 4, 5, 6, 7, 8, 9 layers. There's a skip a connection right here. At this point, we output the density. So this part here focuses on the 3D geometry. We give it the view dependent angle of the camera, and this part right here, which is very small, focuses on the view dependent appearance. So that extra trick that needs to be done is actually we need to transform the input before feeding it to the model. Why is that? If we feed in the XYZ coordinates right away into the MLP, we're gonna get this smooth looking result. And that's because MLPs, they actually tend to favor smooth, low frequency functions. You can think of low frequency functions as low level details. So they're not gonna be able to find these very sharp, fine detail type of relationships. And the reason is because the MLP, the gradients that are learned at the beginning, the gradients that are larger at the beginning, they happen for low frequency patterns. So the model is going to learn those low frequency patterns first, and the high frequency ones have very low gradients, so they're learned later, if at all, depending on the capacity of the network. There's also activation functions like the ReLU. Those that introduce smooth nonlinear transformation. So the span where the input can vary is very small in an MLP. So we want to force the MLP to learn high frequency functions. So we're going to be transforming the input space into something that's more complicated. And we do that using the Fourier transformation. So we're just going to pass these coordinates into a bunch of sinusoidal and cosine type of high frequency function. And by introducing that, we're going to improve the gradient flow, and we're going to make it easier for the network to learn complex mappings, since the encoded input is going to span a richer space of variation. So we're going to force the MLP to learn these high frequency variations right away. So it's going to be able to output fine detail in the texture, those sharp boundaries, all of these lighting effects. One last thing to mention is these view dependent radiance. So for example, this point right here and this point right here are the same point in 3D space, but viewed from different angles. And so what this shows is that this shows for the same pixel, sorry, for the same point in 3D space, this is the kind of radiance distribution you can expect depending on the viewing angle. So this is what NERF is about, and thanks for tuning in.